Hello, this is the second video of the Algorithm 1 series for OCR Discrete Further Maths. It looks at algorithms that use pseudocode. Pseudocode is a cross between statements in English and computer syntax. Therefore, it consists of concise, unambiguous instructions that could form the structure of a computer code. Common sense should be applied to these instructions, which are split into numbered lines for easy reference and adaptation. No particular computing language or syntax are used, but sometimes algorithms are written in pseudocode first in order to help to decide what programming language to use. Some of you may have come across pseudocode in Key Stage 3 Computer Science. Here is an algorithm and the pseudocode equivalent for the area, diameter and circumference of a circle, calculations that you will be familiar with already. You will remember that the area is pi r squared, that the diameter is twice the radius, and that therefore the circumference is either 2 pi r or pi times the diameter. If you read through both the algorithm and the pseudocode, you can see that they are essentially saying the same things in the same number of steps. There is a slight difference in terminology, but that is all. Note that both of them have an end, stop or terminate instruction. You may wish to pause here to try out these algorithms and pseudocodes for yourselves. Here is another algorithm, which is written in pseudocode and gives an estimate of a value of a constant e. If you are not yet familiar with the number e, pause now and find it on your calculator. You will see that there is a button with ln or ln or a natural log. The inverse function will be e. Set the value of the number to be 1 and you get e to the 1 equals e, and this will give you the value of that constant. In the pseudocode, you will notice that it's written in steps of 10. This is because sometimes in computer programming, when people go back to their code, they need to insert additional lines. And then in that case, if it's in steps of 10 previously, they don't have to renumber all the other steps. You will also notice the use of the word let. When we say let a equal 1, b equal 1, c equal 1, for example, that means that's what we're using as those initial inputs. Additionally, when we have, for example, step 50, let b equals b plus 1, we are using b, therefore, as a counter. If we were to trace the algorithm using a table, you could see that step 10 we have started off with a, b and c equal to 1. In step 20, c equals c times b, 1 times 1 is 1. We will then let a equal a plus 1 over c, which in this case gives us 1 plus 1 over 1, giving us the answer 2. Step 40 does not apply in this case because b is still only 1, not yet 4. B will then become, though, a 2 value in step 50. Step 60, we go back to step 20, so this is where we have this loop being formed. So, back to step 20, let c equals c times b, we would have a 1 times 2, which would give us a 2. Then, in step 30, we have let a equal a plus 1 over c, which would give us 2 plus a half, which could give us a value of a of 2.5. B then becomes a 3. We go back to step 20, and c becomes 2 times 3, which is 6. After that, a becomes 2.6 recurring, as we add that 1/6 to the 2.5. B then becomes 4, C is now 24. A becomes 2.7083 recurring. At which point, because B is 4, we go to step 70, which means that we are printing this value here, that E is approximately equal to 2.7083 recurring. It doesn't in this case state the accuracy that we need to use, but if it was to 3 significant figures, that would therefore be 2.1 to 3 significant figures. At that point, we would stop. Some of you may be wondering how E is calculated in this way. There is a series that you won't have met yet, which says that e to the x is approximately the sum between 0 and infinity of x to the n over n factorial, which would give us 1 plus x over 1 factorial, which is just 1, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4 over 4 factorial, and so on. In this particular example, when x equals 1, e to the 1, which is equal to e, will therefore approximately be 1 plus x being 1 plus a half plus a sixth, 3 factorial being 6, plus 1 over 24, 4 factorial being 24, plus and so on. And that is what this algorithm has actually worked out. It's an algorithm that works out the compound interest received on an initial sum of money after 8 years. You will note that it is an iterative nature. In other words, it's looping to repeat some part of the code. For example, for step 20, for I equals 1 to 8, when we get to step 40, it says next I. So in effect, we loop back to step 20. You should be able to see that the initial sum invested was 500, let's call them pounds, so £500, and that the interest rate is 6%. We can extract this information from the algorithm from step 10 and step 30. The purpose of a variable I is to act as a counter or to give us the loop for the number of years we are going through. What is happening as we go through the loop is that each time we multiply by 1.06. Therefore, after the 8 years, we would have £500 times 1.06 to the power 8. You will note that it only actually prints A after we have run through the loops for I 1 to 8. If we were to use a recursive algorithm in comparison to this iterative algorithm, then it would call upon itself again to repeat the code. For example, if we were calculating n factorial, an iterative algorithm would involve looping through integers 1 to n, multiplying as it went along, whilst a recursive algorithm would use the product n factorial equals n minus 1 in its code, thus coming up with a neater and more elegant solution, i.e. less code for the result that we wanted. One of the things you may be asked to do is to adapt an algorithm. In the next session 1.3, we will look at algorithms for bin packing.